In this lesson, we are going to look at inductive reasoning, conjectures, and counterexamples. So what is inductive reasoning? So inductive reasoning is making a conclusion based on observations and patterns. So let's get that written down. Next, what is a conjecture? A conjecture is a concluding statement reached using inductive reasoning. So let's get that written down. So let's think about this another way. Inductive reasoning is when you make a conclusion based on what you see, the patterns and what you're observing. The conjecture is that concluding statement that you make at the end that says, this is the conclusion I made based on what I observed and the patterns that I saw. So let's look at some examples of this. So what you're doing in these is you're looking at this number sequence or whatever sequence you see, and you're saying, is there a pattern that I see that's going on? What do you observe? What patterns do you see? And from that, you're going to write a conjecture that says, this is what I concluded based on the pattern that I found in these numbers. All right, so looking at number 1, 38 to 31, 31 to 24, 24 to 17, what did you notice? If you notice that they were going down by 7, just like me, then this is the sequence that you would have found. So I'm going to write this first one as a conjecture so you can see how it's written, and then you can help me write the next ones. So to generate the next term, that's what I'm going to say first. To generate the next term, what did we do? We subtracted 7 from the previous term. So I'm going to put it as, to generate the next term, subtract 7 from the previous term. Right? So that's how, it's like an instruction to someone just randomly reading this, or you give it to someone else and they need to be able to know what to do based on your conjecture. So now look at number 2 and see if you can figure out the pattern that's taking place before I get to it. All right, pause it if you need to, but now we're going to look at what this pattern is and see if you got it. Okay, so this is the pattern that I saw. I saw that if I doubled 2, I'd get 4, and if I added 1 to that, I would get 5. If I doubled 5 and added 1 to it, I would get 11. If I doubled 11 and added 1 to that, I would get 23. Do you see how I found that pattern? Hopefully you were able to see it too. So now we have to write the next 5 terms in this pattern. Double 23, add 1, you get 47. Double 47, add 1, we get 95. Now double 95 and add 1. 191 is what you should have. Then double that and add 1. $383, and now we want to double that and add 1. To get, what do we get? 767. All right, so now that we have that, we can write our conjecture. So because we're creating a next term, I'm going to write first to generate the next term. Remember, think of it as like instructions you're giving to your friend. So to generate the next term, what did we do? Well, we doubled the previous term, and then what else did we do to it? We added 1 to it. So now let's look at number 3 together. So I want you to take a few seconds, pause it if you need to, but see if you can figure out the pattern that's taking place with 3 without me first. All right, so hopefully you took a few seconds to figure this out. This is the thing that I noticed. I noticed that the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and the square root of 16 is 4. So what I noticed is that they are all perfect squares. Did you catch that? So keeping that in mind, what are my next 5 terms? Well, 5 squared is 25. 6 squared is 36. Then we're going to move on to 7 squared. Then we're going to do 8 squared. And then we're going to do 9 squared. So now, how would you write this as a conjecture? Think about it. So this is how I wrote it, using a little bit of the math language. Each term is a perfect square. That's my first statement there. And so after this, I'm going to use the nth as my math term. So to find the nth term, n stands for the number term, if you will, then what you have to do is you have to square n. So to find the nth term, square n. So now try 4, 5, and 6 on your own. See if you can recognize the pattern and write a conjecture. And we're going to come back and we're going to look at these one at a time. Okay? We're going to move on to a counterexample. So what do you think a counterexample is? Well, a counterexample is an example that shows a conjecture is false. So if you make a conjecture, that conclusion, the statement, and it is false, you need to make a counterexample. So basically saying, why is it false? You can't just tell somebody it's false. You got to be like, well, why is it false? That's your counterexample. So we're going to look at some conjectures. We're going to determine if they're true or false. And if they're false, we're going to provide a counterexample. Remember, you can't just say something is false. It's like, well, why is it false? Counterexample is the why. So looking at number 7, the sum of any two consecutive integers is always odd. You have to determine if that's true or false. It's basically saying 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 4 is 7. Is that always odd? Am I ever going to get an even number? No, I'm never going to get an even number if I add two consecutive integers. So this is a true conjecture. So now looking at number 8. The product of two numbers is always larger than either number. The product means multiplying, right? So if I multiply two numbers together, is it always going to be larger than either number? And when it says either, it doesn't mean both, it just means one or the other. So think about that. Is that true? If you got false, then you're correct. It's not true. And I can't just say false though. I have to prove that it's false. And so that's what I'm going to do. I'm going to prove it's false by creating a counterexample. In my counterexample, I found that if I multiply 2 times 1/2, I'm going to get 1. This is actually true of any number. When you multiply it by its reciprocal, you're going to get 1. 1 is smaller than 2, therefore it's false. Another good example would be any number that you can pick times 0. If you multiply any number by 0, it's 0, which is also smaller than one of the numbers. Therefore, I've proven it false. So now that you know what a counterexample is, go through 9 through 16 and see if you can determine if they're true, false, and if they are false, what is a good counterexample for that false statement.